Pop quiz. In the reaction between acetic acid and ammonia, which species acts as the base? Is it A, acetic acid, B, ammonia, C, acetate ion, or D, ammonium ion? Lock in your answer. We will reveal it in the video. In this video, you will learn the Brønsted-Lowry model for acids and bases, how to spot conjugate pairs, how to draw the curved arrows for proton transfer, and how to predict products, fast and confidently. Here is the big idea. Brønsted-Lowry acid donates a proton, while a base accepts a proton. When we say proton, we mean an H+ ion. A proton transfer looks like this. The base's lone pair reaches for a proton, and the electrons from the HA bond transfer to the A atom. The result is a conjugate base, A-, and a conjugate acid, Hb+. Time to reveal the answer to our pop quiz. When acetic acid reacts with ammonia, the ammonia accepts the proton and forms the ammonium ion. That means ammonia is the base, and acetic acid is the acid. So the correct answer is B. The products are the acetate ion, which is the conjugate base of acetic acid, and the ammonium ion, which is the conjugate acid of ammonia. Here is the language of pairs. When an acid donates a proton, it forms a conjugate base. When a base accepts a proton, it forms a conjugate acid. Because proton transfer is reversible, we often draw equilibrium arrows. Water can act both as an acid and a base. With a stronger acid, water acts as a base to form the hydronium ion, H3O+. With a stronger base like ammonia, water acts as an acid to form the hydroxide ion, OH-. The property of substances to act both as an acid and a base is called amphoterism. Here is a quick guide. First, draw an arrow from a lone pair or a bond to the proton. Second, show the original proton bond's electrons moving back to the atom that loses the proton. Third, check charges. Bases gain a positive charge. Acids leave behind a negative charge. However, please do watch out for these traps. 1. Bases are not only found in hydroxide groups, as lone pairs on nitrogen, oxygen, and sulfur can act as bases. 2. A proton is not a neutral hydrogen atom. It is the ion of hydrogen, H+. And 3. An acid's strength and rate are related, but not identical ideas. So far, we've got the model, the arrow rules, the conjugate pairs, and water's two hats. Ready to lock it in? Tap the link for study guides and flashcards on this topic, so you can keep learning without missing a beat. Now let's apply what we've learned so far. Methoxide ion is a stronger base than phenoxide ion, and phenol is a stronger acid than methanol. So methoxide ion pulls a proton from phenol to produce phenoxide ion and methanol. The reaction goes toward the side with a weaker acid and weaker base, which is the right side in this case. Here is another case. Bicarbonate ion accepts a proton from acetic acid to form carbonic acid, which quickly decomposes to carbon dioxide and water. The gas leaving the system helps pull this reaction forward. Here are a few refinements to keep in mind. The solvent can either help or hinder proton transfers. Steric crowding can slow down the approach to the proton, and resonance can stabilize conjugate bases, which in turn strengthens their corresponding acids, like the acetate ion from acetic acid. Now, let's walk through the steps together. Step 1. Identify the most acidic proton. Step 2. Find the available lone pair or basic site. Step 3. Draw the arrows, one from the base to the proton, and another from the breaking bond back to the atom. And step 4. Label the conjugate acid and conjugate base. Then double-check the charges to make sure everything adds up. To recap, acids donate protons, bases accept them, and each reaction makes a conjugate pair. Use arrow etiquette, remember water can play both roles, and predict direction by favoring the side with a weaker acid and weaker base. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.